Alright, matrix multiplication. This is section 4.3 from our Algebra 2 classes. The first type of multiplication we're going to talk about, even though this section's about matrix multiplication, this topic's a little bit different. It's called scalar multiplication, and it follows your common sense. When you see 3 being multiplied, this is called a scalar. So when you see a plain old number being multiplied times a matrix, then it follows exactly what you think. It's like the distributive property. Everything inside the parentheses gets multiplied by that value. And so you get these values on the inside. That is as difficult as that one gets. Nothing is harder about that. So scalar multiplication has a lot of the same properties that you're very used to. Let me show you from the book, page 179, shows you all those properties, and I might have to zoom out a little bit. But, here we are. We're looking at these properties. Basic things like closure if you multiply. So if A, B, and O are n by n matrices, so they all have the same dimensions. And C and D are different scalars, so they're just numbers. Then CA is an m by n matrix. So if you multiply, like we just had a 2 by 2, and we multiplied by a number, and we ended up with a 2 by 2. So in other words, it's a closed group. And I know that doesn't make a whole lot of sense to a lot of you Algebra 2 kids, but you didn't end up with some other weird dimension matrix, which is not going to be true when we get to matrix multiplication. So, hold on to your hats there. The associative property works, and the distributive property works, and you can multiply by the number 1 to any matrix and it stays the same. That's called the multiplicative identity. And then the multiplicative property of 0, when you multiply by 0, then if everything turns into the 0 matrix, which is a matrix that has all zeros in it. Okay, that idea kind of makes sense, I'm sure. Okay, so we can extend our ideas of solving matrix equations even further. So for instance, we've got this matrix equation to solve, and just like I kind of showed a little bit in class yesterday as far as how I dealt with these types of problems, I will distribute the 2 inside here, and so what would I end up with? And because it's positive, I'm going to end up subtracting this, so I'm going to show you kind of 2 things at the same time. Subtracting 2 times 3 is 6, 8, negative 4, and 2. And we're going to subtract that matrix to the other side as well. Like we did yesterday in class, if you want to just put it on the other side, like over here somewhere, and cross this part off, that is also an acceptable way to handle it. But you're right, all of this is going to cancel. And so you're going to be left with 4x on this side. And here I have 10 minus 6, which is 4. 0 minus 8, negative 8. 2 minus negative 4, well, that turns into addition, so that would be 6. And 2 minus 2 is 0. And then this is where we're talking about scalar multiplication again. We're going to multiply by the reciprocal of 4, which is 1/4. Both sides of the equation get that so that we have not changed the balance of the equation. So matrix X is the matrix 1, negative 2, 1.5. When you take 1/4 of 6, you get 1.5, and 0. So there is your matrix that we called X. So that's so we've kind of extended our idea of solving matrix equations. Now we need to turn our attention to matrix multiplication, which is much more difficult. So it is not what you think it is. It is not simply multiplying corresponding elements like this one times that one, and this one times that one, and this one. For the kids who are not listening and not paying attention and want to do that in my classroom, on quizzes and tests, you're going to lose all the credit because that has nothing to do with matrix multiplication. So let's take a look at what matrix multiplication involves. There are 2 rules that apply to matrix multiplication that you need to know. Now, there's no book that calls them this. These are kind of my made-up names for them. But I call it the inside number rule and the outside number rule. Now, the first thing I need are the dimensions of each matrix. This is a 2 by 2 matrix. This one is also a 2 by 2 matrix. Okay, so over here I'm going to write those down. 2 by 2 and 2 by 2. The first thing I'm going to look at are the inside numbers. Now, in order for me to be able to do this problem, the inside dimensions must be equal. Okay? So, matrix multiplication exists if the inside dimensions are equal. That's the columns of the first and the rows of the second. If those don't match, we are not doing this problem. We're going to write down impossible, can't do, inside number rule, violated. Something like that. Okay, and once we get the hang of the matrix multiplication, you'll see why. The outside number rule, okay, let me write those dimensions again, 2 by 2, 2 by 2. The outside number rule tells me the dimensions of the answer. So, the product of these two matrices will have the dimensions of the outside numbers. That would be the rows of the first and the columns of the second. Rows of the first and the columns of the second. So, knowing this, let's just take a look at, before we get back to example 4, let's just take a look at this. I'll come back to that example here in a second. Yeah, let's just do this. Is A, B possible? Well, A is a 3 by 2, and B is a 2 by 3. So the big question is it possible? Well, according to the inside number rule, I take a look at these, and I say yes. Okay, so yes, it's possible, because these are equal. If so, what are the dimensions? Okay, well, that's all about these values right here. So my answer, so AB would be a 3 by 3 matrix. AB would be a 3 by 3 matrix. Now, we're not going to multiply those at the moment, but that's what we would do. All right, so let's say we reverse it. We go with BA. So B is a 2 by 3 matrix, and A is a 3 by 2 matrix. Is this even possible? Well, according to the inside number rule, the answer is yes, because these are equal. If so, what are the dimensions? Well, according to the outside number rule, this is BA is going to be a 2 by 2. So, the big question I have for you is matrix multiplication commutative? What does commutative mean? The word commutative means switchable. Can we switch those? The answer is no, we can't switch those, because obviously, take a look at what we just said. AB ended up being a 3 by 3, BA a 2 by 2. Those are not equal matrices. We said equal matrices have to have not only the same rows, but the same columns. And these clearly do not. Okay, so let's actually look at what does it take to multiply two matrices together? Okay? So we have -1, 0, 3, -4, and -3, 3, 5, 0. Okay, we're multiplying these two matrices together. I want to know what happens here. Alright, now, this is going to seem weird, so you better follow along. Okay? I'm going to take this row of numbers and multiply times this column of numbers. So row 1 times column 1, and I will give you a little bit of color here so you can tell what's going on. So -1 gets multiplied times -3, and 0 gets multiplied times 5. -1 times 0, and, oops, -1 times -3, I shouldn't have said that, and 0 times 5. Now these numbers are going to get added together. Now this is a 2 by 2. Maybe I should have backed up and said this is a 2 by 2 and this is a 2 by 2. Is it possible? Well, the answer is yes, and because the inside dimensions are the same and the outside dimensions are going to give me a 2 by 2. Well, a 2 by 2 has 4 different spots for values. You just found the first one. So if in my simplified final version of this, we just found out that 3 plus 0, the very first entry of my matrix is a 3. Now, you'll notice that I'm using rows of the first and columns of the second. So row 1 times column 1 gave me the row 1, column 1 entry. Alright, now stay with that. Stay with that column, or that row, and now we're going to multiply row 1 times column 2. Row 1 times column 2. We're going to do like fashion, right? The -1 is now going to get multiplied times the first entry, and the 0 gets multiplied times the second entry. So we have -1 times -3, or positive 3, I should say. That's positive 3. And 0 times 0. And when we add those together, we get -3. Alright, now we've taken care of the top row. Now we need to go to the next row. Alright? So we have second row, but now we're going back to the first column. Okay? The first column. So we have 3 times -3, and I think that might be hard to read now that I've colored it twice. 3 times -3. And -4 times 5. And we're going to add these together, and we get -9 and -20, so this is -29. And now we're going to the second row and the second column. So this row times this column. Let me make those darker. Maybe it's a little easier to see if I make them darker. So 9 plus 0, right? 3 times 3 is 9, plus -4 times 0, which is 0, giving me just plain old 9 for that last entry. So I know that we're going to have to do a lot more with this matrix multiplication so you can understand what these numbers are, but it's always rows of the first times column of the second. Rows of the first, column of the second. Then move down to the next row, column 1. Next row, column 2. Whatever entry you're looking for, if you're looking for row 2, column 2, that's what you're going to multiply together, row 2, column 2. We will practice in class because I know you'll have lots of questions and you'll need to know more about it. And 4 by 3, I want you to take a look at these properties on page 182. Last thing. You could take a look at it and see what's going on. These properties are true, associative, distributive, all these good things. The one that's missing is the commutative property.